Welcome back to our open source chip design and verification event. As we witness the power of open source lint solutions to address problems left unaddressed hitherto by commercial solutions, we now have our partners from Tessolve to take this to the next level. Mr. Marmik Soni, a senior design lead at Center of Excellence Tessolve and Dr. Mike Bartley, PhD, will deliver this session. Dr. Mike is a senior vice president at Tessolve UK. The title of their talk is Enabling AI in Chip Design Through Open Source. We are pleased to host our partners in this event and encourage innovation in chip design and verification through open source tools and flows. Let's listen in.
On AI strategy for DV, design verification flow, and a test bench TB AI tool. I'm Mike Bartley, I'm the SVP, I'm running the Center of Excellence COE for Tessolve, and I'm also joined by my colleague Marmik Soni, who will also be presenting part of this. Okay, so here's the outline of what we're going to talk about. We're talking about AI strategy, our AI design verification flow, some tools to generate test benches using AI, some of the tool features, and we've got a lot of AI DV in our ecosystem. We've put together a lot of tools. Okay, so here's an example of one of the tools which we're looking at the moment. We have from spec input from a Python generator, we're actually able to generate a test bench, and that's a Python test bench. A lot of people know CocoaTB, which is a Python simulation tool, and running with Verilator. And the key thing is both of those are zero license. Okay, so we can generate effectively a Python test bench, which we can run on Verilator, and therefore we can run effectively with zero licenses. That allows us to run a lot of simulations in parallel, and that allows us to build the data set needed for the machine learning algorithms. Obviously, a lot of people already know AI machine learning requires large data sets. Okay, so we've gone for a flow where we use Python test benches, which we can compile and run on a Verilator test bench using an RTL design. That could be Verilog or System Verilog or VHDL. But we can compile that on Verilator into a binary, and then effectively we end up with a binary that can run across multiple machines. We generate simulation data from that, and that goes into our machine learning process. You can also see there a System Verilog UVM flow that goes via QuestaSim, and that allows us at the end of the process, once we've tweaked the test bench to give really high coverage, or whatever is our target, can run on QuestaSim to validate what we've achieved on Verilator and Python. Okay, so that's an outline of one of our tools. Now, one of the key things which we've done in our AI strategy is make sure the models are replaceable. So if you look at the diagram here, okay, and if you just quickly flick through there, we keep our training data separately, and we can run that on a model. Okay, and if we go through here, one of the other key things that you need as well as the training data is the user prompts. So we record those as well, and effectively there we can train our model using a database of training data and user prompts. Okay, and then we save some of that test data for validation of the model. Once we validated the model, then we can be using it to generate results. So there we can start putting in real inputs, and we can start to see the results. Now the key thing here though is that if we see a new model, so for example ChatGPT comes out with a new version, or we want to move to a new app that's just come out in China, for example, which is very relevant at the moment, we can take those untrained models, and through our automated training data and user prompts, we can quickly generate a new model. We can validate it through our test data, and then we can just start to generate new results. We've done that quite a few times, and typically when we do that, we see an immediate improvement of the results, and we can do all of that very, very quickly. One of the key things, as well as doing these replaceable models, is to maintain security. Okay, obviously these data sets contain a lot of secure data that we don't want to leak out, so we maintain that. But there's also been a lot of reports in the press about reverse engineering models to get back to that training data. So again, also we make sure that the trained models are also kept secure, and quite often they're in the cloud under secure situations in the cloud. Okay, now we've done a lot of this work internally within Tessolve, and what we found the most effective way of getting the level of innovation we need is to what we call innovation at the edge. So we've got a central team of experts who know AI, know how to train models, and know how to deploy this. But across Tessolve, we've got a number of divisions. That might be finance, it might be HR. We've got a number of business units as well in test, embedded, PCB, real SI. And what we found is they know the types of automation they want. Okay, they know best what the types of support they want, what types of automation they want, and where they can best deploy AI. So what we've done from the center is deploy all this, but let the business units and the various internal divisions, such as HR, such as finance, then automate themselves. And that's what we call innovation at the edge. Okay. In terms of DV, which is what we're going to be talking about today, and that's on the next slide, please. Okay, we've done a lot of experiments. So across the top there, you can see our typical flow. We start with requirements and specification. We generate a feature list from that. Okay, and then from that, we generate a coverage plan. Then we need a test bench with lots of agents. Once we've got all that working, we start to write tests. And that allows us to start running simulations. Then we start to constrain because we want to hit corner cases. We want to hit functional coverage. Okay. And then once we've got that functional coverage data, we can start to try and automate coverage closure. So we want to automate as much of this flow as we can. And what we found is that at the front end, we can deploy AI very well at the front end to do feature extraction and coverage planning. We can automate test bench generation using AI, and we've done that. We'll show you some good examples of that. But if you want a more sophisticated test bench, we're finding that what we're doing is combining AI with Python generation, and that gives us a more sophisticated test bench. Okay, and also for tests as well. So some of this is just automation using things like Python. Some of it is using AI, such as generative AI. We use a lot of generative AI from some of those online tools which you've probably heard of, like as I say, ChatGPT. Okay, and then obviously to get the coverage data, you're running lots of simulations. And trying to close the coverage. Debug as well is quite interesting. There is a lot of AI ML being deployed to debug. A lot of it's coming from the EDA vendors, Synopsys, Cadence, Siemens, and they can actually look at a large database regression result. They can pick out the failures and they can start to group them. So you may have 100 failures, but they say actually these 30 all probably come from the same bug. These 40 come from the same bug. And then they can focus those 30 and 40 failures. And then they can say, and here's the one with the shortest simulation time. That's going to be quicker for you to debug. Okay. And by the way, these were the check-ins that happened. And this was the most likely check-in that caused this bug. And then they can focus down your debug efforts. Okay. One other thing which we're doing is a test bench generator for designers. Okay. Now you think, well, designers need to be independent, but quite often designers want to just do a quick simulation of those designs. So rather than just throw RTO over the wall, they want to do some simulations. But quite often, a lot of that is just thrown away, and it's quite a lot of effort for a designer to do it, and they do limited simulations. So what we're doing is that we can generate them a test bench, either a simple system Verilog test bench, or we can generate them a more sophisticated UVM. Depends on the sophistication of the designer. We can generate that for them automatically, and then they can do some more sophisticated simulations on their design. Okay, and they can add knowledge as well. So if they're running on they can add assertions, for example, then why not use them? Okay, now you may think, well, that breaks independence, but as long as the verification engineer is not relying solely on assertions written by a designer or functional coverage written by the designer, they're following their standard flow. So, for example, they're generating their own functional coverage model, but the functional coverage from the designer is just additional. A lot of this really works very, very well. And this generation of the test bench automatically for the designer will increase the quality of what they're passing to the verification team, and therefore ultimately improve the whole verification flow, because you're getting higher quality RTL from your designers. And here's the flow. You put in the spec and you put in the RTL, and it will generate a test bench. We use our Verilog compilation there, as you can see. And if the number of errors is less than 3, then if there's no errors, you can go straight to simulation. If there are more than 3 errors, you can go to Verilog and you can repeat that. If there's less than 3 errors, we find that manually you can typically fix those errors and go straight to simulation. And this goes around that loop, and it goes around that loop. And you say, well, you got a spec, why are you inputting the RTL? Because this is not a sign-off process. Care about submitting the RTL to generate the test bench. Okay, it's not a sign-off process. It's just allowing designers to run some simulation before they hand it over. Okay, so I'm going to hand over now to my colleague Marmik, who will introduce himself as well. Hi, Marmik.
The tool that Mike introduced is just there. If the errors are not there in the compilation through our open source tool, it will be giving the simulation results. And if the errors are there, it will be automatically reprompting the AI model, and it will be generating the test bench again with the modification, with the correction. And there it will be giving us the simulation results for the given RTL. Tool, RTL design. So this is how the tool is looking like. So RTL details and the designer knowledge is given to the tool. Then after it will be generating the test bench like this. And it will be also having, so it is very simple example that we have taken over here. It is the linear feedback shift register. So for this example, when we are uploading the RTL and the designer's basic knowledge, basic information, then it will be generating the test bench, and if it will be trying to compile it error-free. If the errors are there, it will be reprompting itself for 3 times, and then after it will be saying that the test bench generation is failed. And in case if it is successfully generating test bench, which is for the simple examples, it is most of the times you are getting the test bench getting generated, it is passing through the compilation and simulation. So we are able to see the simulation also. So in this process, we have incorporated the open source tool only. So for compilation, we are using iVerilog or Verilator, and for the simulation, we have used the GTK wave. So the tool is designed at Tessolve only, and it will be giving us the simulation results also completely with the use of AI models, as well as trained AI models, as well as the open source tools. So what are the features and benefits of doing this? So as Mike explained, designers are looking for the first cut test bench generation at independent test bench generation. So there, this tool is going to be helpful. It is quickly writing within a fraction of time. It is writing the test bench, and it is having the tools, both the tools integrated. So even you're not required to use the tool, it is inbuilt in this tool which we have generated. So iVerilog, GTK wave, they are inbuilt in this tool. So it is helping the designers to have the easy debug of their RTL. So the features are AI test bench generation. So no need to write any test bench for the basic initial test at the RTL end. It is having the error feedback. So compiler, whatever error it is throwing compiler, the same is used for the reprompting. And so no manual prompts are required. It will be the generated error by the tool itself will be given to the AI tool, and it will be generating the correct test bench after that. So the tool chain is having the integration with AI model and the compiler, and also we are having the feature to view the waveforms with the simulation. So what are the benefits of this kind of tool? So it is handling the error by itself for the basic test bench. It is accelerating the designer's basic smoke test kind of verification. It is accelerating that process. It is not requiring every time to go to the DV team and getting the RTL checked. It is saving a lot of time when a complete test bench is being written and it is again getting corrected with the error log. So it is saving a lot of time for the tool integration saves a lot of time. So people are not required to open GTK wave or not writing any command they will have to run for the open source tool. The tool itself is having the buttons where people are clicking those, and without any commands or any prompts, they are getting the outcome in the form of waveforms. So all the tools that we have used here are open source tools. So that is quite effective and cost effective for the people to use this tool. So the idea which Mike was explaining in detail with the flow, Mike will be explaining that here. That will be for the coverage improvement using ML and open source. Over to you, Mike.
Okay. So this is for specifically aimed at coverage improvement. This is actually a lot more complicated to do. Generative AI that we use on the specification to generate feature lists or test plans or test bench generation. Okay, trying to close coverage. Closing coverage takes a lot of effort in the project. So anything we can do around that, we'll see if we can improve that coverage improvement flow. Okay, so here you can see on these test benches here. Again, this is what we showed you earlier. We've got the test benches with knobs, configuration, and parameter settings. Next slide, please. That generates the Python UVM. I explained this before, and that will go through a validator. It will generate a huge amount of data for us. And what we're specifically looking at with this flow, showed you before generic flow, we're now looking at a verification score. We're now looking at coverage. And that's the metric we're trying to improve. And that's the target for our machine learning. We need machine learning will need a loss function in order to do its learning. So we know what we want to achieve, maybe 100%. If you've got 85%, then our loss function says it's 15%, okay? And that can then feed back into our machine learning. And we use things like gradient descent, where we're trying to get to the minimal number through gradient descent. We can use genetic algorithms. And what they're trying to do is tweak all those configuration bits, those knobs, those parameter settings in our test bench to try and get the best combination of those. And there could be anything up to 100, 200 knobs, configuration, parameter settings, etc. We're starting out on this with much fewer than that, but what we're trying to do is then say, here's the top 10 configurations. We can pass that across to an SVUVM training environment, and it's the same test bench. So whatever the UVM test bench that we generate, we can generate it in Python, and we can generate the same in SVUVM, and then we can take that to a Questus flow. And that's more, and that's the other simulators, Cadence for Synopsys as well, obviously available. And that gives us a sign-off, if you like, with a known tool. And that's our flow, and that's what we're working on at the moment. And we're working on lots of different tools here. We're looking at register extraction, test case generation, assertion generation, functional coverage generation points, unit test bench generation. We're working on all of these. And these are the types of tools that we're developing. A certify, right, assertions, obviously, a spec extraction I've talked to you about. There's a tool that will automatically review your UVM test bench and give you feedback and suggestions for improving your UVM. And we've got UVM training tools as well. As you can see there, that CocoaTB converter tool. CocoaTB is our Python test bench. But we're actually doing some of this on physical design as well. So we've got a PDK training tool with those design kits, and we're actually working on a library for that as well, and we've got the test bench generators as well. So we're doing a lot across VLSI, and more specifically DV is where the focus is, but we're also doing some physical design work in AI. Okay, so thank you for listening. Myself and Marmik are always available. You can see my contact details there. Always feel free to contact me. We're partnering with a lot of companies on this, so at the moment we're not charging for this service. We're very much in a learning phase and a partnering phase. So we're partnering with about 5 or 6 different companies. We're trying this out, and we're all trying to learn to try and work out what's the best way of deploying artificial intelligence and machine learning in design verification. Thank you very much.
Thank you. Thank you, Mike. Thank you, everyone.